Record. Hey kids, this is Mr. Pickett. What I want to do is I want to talk about our notes on Classroom in case we don't get through them on Wednesday when I'm here, and then get you guys kind of tuned up for your harmonic motion lab as well. And so you should be on page 105 in your physics textbook. I'll open that up here as well. I got to find it. And then I'm going to share my screen, so I'll just do that right now. Screen sharing, so you guys should be able to see this. Let's go to student. Unit 1. And like I said, we should be on unit 5, page 105. So I'll move that way. And here we go. So there's hopefully not a lot of new information on here. I hope a lot of this was getting to use the physics equipment to understand Newton's second law, which I think a lot of us have a good understanding of. What we're taking a look at from your how does push and pull affect the motion of a cart? You were basically trying to find a relationship between your application force and also what ended up happening with maybe the velocity or the acceleration. And so as we take a look at these kind of three graphs superimposed onto each other, you should recognize that when you have places where you have like no force acting on the object in a weird capacity or little force, you should have your highest velocity. And so and that seems counterintuitive, right? Where you have almost no force acting on the object is where it's moving the fastest. And then where you're having the most force acting on it is, if we go down here, is or a lot of force, acting on the object is where you're having places where the velocity is actually rather low. And again, that seems kind of counterintuitive, but you got to remember the motion of the object was kind of back and forth. And so when do you think you're going to have the most force acting on an object? Well, it's when you have to start it and stop it, right? Right on the edges where your velocity is zero, where you're having to apply the most force, or you have to start it up again. And then as we take a look at acceleration, we should recognize that when you have a lot of force, you should also have a lot of acceleration. And so they're directly related to each other. They might not have the same numbers, but the graphs share a very similar pattern as well. And you can see the directly proportional word. Now, if you haven't done this, right, by the way, what's really cool is within that force and acceleration graph, if you change log or pro and you actually put those things against each other, where you have applied force and acceleration and you graph them next to each other, you're going to get this crazy squiggly line. So I'm going to try to make sure I show that with you guys yesterday. So I'm recording this on Tuesday night. I'll see you guys Wednesday. I'm hopefully going to remember to talk to you guys about this tomorrow. So what is the relationship between applied force and acceleration? Well, the applied force is pretty simple. If we look at this, acceleration and force have a direct relationship. Nothing new. Now, how does friction affect this? I'm not going to have you guys do the next activity where you're pulling somebody, but friction absolutely has an impact. We have to start thinking about friction as potentially taking away some of the force that we're applying. But eventually when the object is moving, not that we negate that that force, but it's going to subtract from your applied force. All right. So again, as a result of friction, more than one force is acting on an object, right? These forces include a constant force being applied, right? Whoever's pushing or pulling. And so you have to think about your net force instead of just somebody pushing. You have to include the applied force or the pulled force and the friction that's acting on the object. All right. So in our next activity, a next lab that you're going to do, which is called simple harmonic motion, you're basically going to, instead of talking about a force that you're trying to keep consistent, you're going to talk about what happens when you have a force that is constantly changing, like a spring, right? It says a mass vibrating on a vertical spring. So you might have a slinky, and then you're going to attach a mass to it, and then it's just going to basically oscillate up and down. All right, so conceptual practice. I'm going to tee you guys up. Make sure you pause the video, potentially as a class or even as a group, so that way you can answer these questions, and then you can compare your answers to what I talk about. So you're pulling a child on a toy sled along the ice this is important, with an applied force that varies. So the person that's doing the pulling is maybe changing the amount of force that they give. So sketch the resulting acceleration in the graph provided. State any assumptions you're making. So state your assumptions now and pause the video. Okay, hopefully you paused the video. So an assumption that I'm making is that there's no noticeable friction. So we're just assuming that the applied force is basically your net force that's acting on the object. So what do we know about, so that's an assumption. Now, based off of that, sketch your resulting graph the shape of your graph based off of the applied force. Pause the video. All right, welcome back. I hope that your conversation with your classmates is that the force and acceleration should be directly related. So the shape of the acceleration versus time graph should match, be very similar to the applied force, meaning that in the first couple seconds, you should see this acceleration increase. And then when your force is consistent, you should have consistent acceleration. And then you're going to see the force decrease for a moment. And so you should see the acceleration decrease. And so the shape of the graph should be similar, not the same numbers, but the shape should be the same as the applied force graph. Okay. Now, number 2, the motion of a car is described by the velocity versus time graph illustrated in figure 9.2. Describe in words the motion of the car. Do that now. Pause video. All right, welcome back. So as I'm taking a look at this, I look at this in 4 segments: segment 1, segment 2, segment 3, and segment 4. I'm looking at a velocity versus time graph. So I recognize that I have consistent velocity in the first segment. I have a decreasing velocity in the second segment. I have no velocity in the third segment. And then I have an increasing velocity in the fourth segment. So hopefully you can see that. So that's the motion of the car in words. Now with B, it says use the graphs provided and your understanding of Newton's second law to construct an acceleration versus time graph, and then applied force versus time graphs for the car, and state any assumptions that you're making in your answers. All right. Pause the video and work through those 2 graphs. All right, welcome back. It's magic time. All right, sorry, I'm going to mess with you guys. So as I'm taking a look at this, hopefully you know that acceleration is calculated by taking your change in velocity over time. And so we're looking at the slope of this graph to help us understand the shape of this. So during segment 1, the slope is 0. So if I have no slope, then I should have no acceleration. So I should have a flat line at 0 in this first segment. Then I have a negative slope in my second segment, and it's a value. I don't know what it is. It might be 1, but it's consistent. So I should see a line go down and then a consistent negative acceleration for a while. Then I have no velocity and it doesn't change. So this should go to 0 velocity as well. And then you're going to see a positive slope because I have a positive slope and velocity. And so I should get an acceleration that's consistent. It's large, so it should move up pretty high, but then be consistent. So it should move like that. Okay. What should my applied force versus time be? Again, they're directly related. And so whatever the shape of this graph looks like, it should look like this. Again, making that connection between force and applied force and acceleration. What's the assumption that we're making? That there's no friction, right? We're assuming that there's no friction that's occurring. All right, let's look at 3. A ball is thrown upward and eventually returns to the ground. As the ball moves upward, is the net force that acts on the ball greater, less than, or equal to its weight? I want you guys to think about, what does weight actually mean? All right, and answer A. Pause the video. All right, welcome back. So hopefully you recognize that the weight is a function of gravity. So it's really talking about the force of gravity. That's what weight is. And so is the net force, the overall force, greater, less than, or equal to the force of gravity as it moves upward? So you got to think about the ball moving, right? It's moving upwards, right? And so we have to think about all of the forces that are acting on the ball. So as it's moving upward, right, the force of gravity is going down. And then which way is friction, right? As the ball is moving upward, which way is friction acting on the ball? If you answered, well, it's moving against its motion, so it's also moving down, what we recognize is that both of those values are going down. So what about the net force? Well, the net force, which is going this way, is actually going to be larger because I have to take the friction, which is going this way, and the force of gravity and add those together. So my net force is actually greater, right, than the weight, because it's the weight and the force of friction, and they're both moving in the same direction. Right, so hopefully that helps you with B. So read B and pause the video. Right, so as you read B, as the ball moves downward, we have the force of gravity going down, and we have friction, which is opposing the motion of the ball, which friction is now moving this way. And so what we see is two forces that are in conflict with each other. And so if we think about the net force is going to be these two things added together, but it's going to be this minus this. And so your net force is actually going to be smaller than the weight force. All right, so justify your answers for both parts. I believe I has. And assume that the force of air resistance may not be ignored. It's important that you read that last part. And if you didn't read that at the beginning, that would have been tough, but that's what the force of friction is. All right, so as I look at number 4, right, use the idealized acceleration versus time graph shown in figure 9.21. Sketch 2 graphs shown below to describe the motion and the net force acting on a toy parachute as it is held some height off the ground and as it falls to the ground. Assume that a plus motion or plus direction is one that is directed downward. Okay, so that's A. Right? Sketch 2 graphs shown below to describe the motion. All right. So as I take a look at this, and I'm just going to go through this one because this is a weird question. I should recognize that my acceleration and my force should look the same. So, or similar. So this should be here. It should move up and down. It should be the same. Now, what about velocity? As I take a look at the velocity, if I'm not accelerating, that means that I am not changing speeds. So I have assuming a constant speed because I'm falling, right? So I'm going a constant speed. So it's going to be a large speed and a constant speed. So boom. Now I experience an acceleration, right? Held off to the ground. Okay. And I experience some sort of an acceleration value. Now it looks like it's a positive acceleration, which that's weird, but that means that I'm going to get faster for a little bit. So I have a velocity here, and then I increase my velocity for a while. So it's going up. And then once I have no acceleration anymore, well, I either hit the ground, by the way, so I could have no velocity, or I'm having a constant velocity again. All right. So this one is interesting here. Describe the motion of the toy parachute in words. So in here, like looking at the information, and I think this is a mistake on their part, but it looks like to me that the toy parachute was falling. Oh, I think I read this incorrectly. Positive acceleration. It's going down. I think we're good here. As I'm looking at this object was falling with a consistent velocity, the same speed, and then it sped up for a little bit consistently, and then it experienced no more acceleration, which means that it's going at constant velocity. That's what it looks like to me. All right. Describe the motion of the toy parachute in words. I did. And then C, I'm just going to not do C. I think C is a poor question, and we're going to skip it. All right, let's go through 5. A bicycle has a mass of 12.5 kilograms, and its rider has a mass of 75.2 kilograms. The rider is pedaling so hard that the acceleration is 0.085 meters per second squared. All right, so they're getting faster. If the rider actually applies a force of 8.8 newtons along the direction of the rider's motion, can the force due to friction be ignored in this case? If friction cannot be ignored, determine what is the force of friction. Right, so I don't know if I can actually write on this. I think I can, But as I'm taking a look at this problem, which I'm gonna see what I can do in terms of changing my screen sharing options. I'd like to annotate. There we go. Boom. So I'm going to draw here, right? So I have an overall mass of about 87.7. So I add these two masses together. So I have an 87.7 mass, or kilograms, excuse me. It tells me I have a resulting acceleration of that. So this is mass, so this is m. I have an acceleration value, not a very big one, of 0.085. And I think what it's asking me is, what can the force due to friction be ignored in this case? Well, I think it cannot be ignored. Well, what do I do? Well, if I take my mass and I multiply it by my actual acceleration, so I take 87.7 and I multiply it by 0.085. I'm going to do that right now. Calculator's right here. So 87.7 times 0.085. I'm going to get a value of what appears to be a force of 7. Roughly 5. Because Newton's second law is force is equal to mass times acceleration. So that's the force, or my net force, that I get out. Now, the writer applied 8.8 newtons of force, right? So what is my force due to friction? Well, my actual motion resulted in this acceleration right here. And so something had to bite or take away from the 8.8 newtons. So it appears that about 1.3 newtons of force has been taken in some capacity, like lost. That is my force due to friction, right? My force due to friction has taken some of the applied force away and basically made it unusable, if you will. All right, so clear all my drawings, exit out of that annotation. Okay, so hopefully this practice was helpful for all of you. I want to make sure that when you guys get set up for your simple harmonic motion lab, that we understand what we're doing. So we have a spring. Don't worry about the spring constant. That's more for me. I don't really pay attention to that, to be honest with you. What you need to do is you need to find a small mass and a slinky, and you need to put them together. I would suggest, right, that you use your table a little bit and that you put a mass and hook it to the bottom of your slinky, and then you add some sort of an index card at the bottom. And then all the way at the bottom of the floor, you have your motion detector. And so what's going to happen is you're going to have this mass that's going to be bouncing very smoothly if you're doing it correctly. And it doesn't have to move quite a bit, just needs to move a little bit. So that way you can create something called harmonic motion. And then what you're going to, and here's your setup. This works out really, really well. Okay. You don't have to necessarily keep all of the numbers the same, but make sure that the mass does not fall on the motion detector. It's happened before. It'll break the detector. So be careful and do the lab, right? The whole purpose of this stuff is to collect some data and then make some predictions and then see what the results look like. The idea is, how are we applying Newton's second law on a spring that vibrates? And then you've got to think about the mass moving. You got to ask yourself, again, the questions of, how fast is it moving, right? In different positions. Like if the mass moves like this, you kind of have these positions that look like in the middle, and they're at the extreme ends as well. You got to ask yourself, what kind of velocity do I have in those positions? What kind of acceleration do I have? And then also, what's my force, right? And hopefully throughout this whole activity, you're going to be able to see those answers and be like, oh yeah, duh, I've seen this before. So enjoy the activity on Wednesday or Thursday, and then get started on this lab Thursday or Friday and keep going. Bye, kids. Enjoy the day.